Hello, everybody. Let's continue the next section of chapter 4, which was about kernels created by either polynomials or power series with positive coefficients. So either we have P of Z, P of Z equals to some n from 0 up to n a n z n, in which a n are positive, bigger than or equal to 0, in which case there's no convergence problem, and we can create Kp, the kernel created by P. We can discuss it on the complex plane, or I mean, a little bit later we'll see we can go even further. So Kp from C times C to C was defined by zero to infinity, and here ZW bar exponent. We showed that this is positive. We even talked about h of Kp and discussed about its elements. The next step was to consider power series. So instead of a polynomial, P of Z is some n from 0 to infinity here. A n z n or a n x n, doesn't matter what is the variable here. And we assume that the radius of convergence here is R2. Radius of convergence. And the reason is that we can define now, we can define Kp as before on ZW, n from 0 to infinity, a n ZW bar exponent n. And this is defined on ZW belongs to disco radius R times disco radius R. That is why we put R2 up there to have dr here. And we also talked about the elements of H of Kp in this case. They are analytic functions on the disk. And if n of z equal to root a n zn are in HP, of course, even HKP. Of course, even if an is 0, they are there, but it doesn't give us any information if an is not 0. Then these are of norm 1 and orthogonal to each other. So this set is an orthonormal set in our space. We can go more and explore more properties of this, but instead let's assure you that you have seen examples of this before, and important examples indeed, without looking at the problem from this angle. We looked from a different point of view, but let's remember those examples. First example, we consider the power series of z equal to some n from 0 to infinity, just zn. All an are equal to 1, or if you wish, 1 over 1 minus z. This case, r is equal to 1. And indeed, we have two interesting cases, or we can change everything into two cases. Either r is finite, where we can normalize it such that r is equal to 1 and talk about functions on the open unit disk, or R is infinity, in which case we talk about functions on the whole complex plane. So both happen. In this case, you have this, and what is our kernel? I mean, we have seen this kernel before. In this case, KP ZW is just 1 over 1 minus ZW bar. We saw this before under the name of Cauchy kernel, sometimes called also Gigot kernel, and H of KP. This is precisely what we had before under the name H2, the Hardy space with P equal to 2. So either you start from the kernel and you end up with this space, or vice versa. Another example 2 is P of Z, so n from 0 to infinity. Not 1, n plus 1 here, n plus 1 Zn. Which is 1 over 1 minus Z. No, sorry, let me write it correctly. Yes, true. If we take an, it becomes this one. And in this case, H of Kp, if Kp ZW is 1 over 1 minus ZW bar squared, and H of Kp in this case is precisely what we called A2 of the Bergman space. And in some books, as I said, they call it also B2 of the notation. It depends on the taste on the author. So it's Bergman space. And the one of them is Hardy space. Both cases are on the open unit disk. Another one which we did not discuss at the very beginning, but indeed several talks in the focus program, they talked about it. It's the case an equal to 1 over n factorial. Zn over e to the z. And in this case, we obtain a space with k of EZW is EZW bar. And in this case, R is equal to infinity. The functions are defined on the whole complex plane. And we obtain a space which is very important in sampling and interpolation. It's called Segal-Bargmann space. So Segal-Bargmann space. I mean, I stay with our notation HKP, but for Segal-Bargmann there are, I mean, I didn't introduce in chapter 1 when we discussed about several examples, but that's indeed a good example to add at the very beginning by introducing some integrals to define its norm. But I mean, in chapter 4, we arrive at the same space from a different route by considering coefficients. So here, 1 over n factorial, previous one, n plus 1, and the first one is 1 here indeed. That, well, yes, I can add 1 if you wish. So the good thing about this approach is its simplicity, anything positive, any AN positive, gives you a kernel, and based on that kernel, you can construct your space. Now, we generalize this construction a little bit more now over series of balls. In the previous setting, our setting was either the complex plane when we considered polynomials. And when we go to series, because of the convergence, sometimes we had to consider something smaller. So it was a disk, sometimes a disk of radius 1 or a disk of radius r. How can we generalize this? In this general setting, I consider X to be a Hilbert space L. So, and it works again for the polynomial case. And sometimes when we go further and consider series, it doesn't work on the on L. We have to consider something smaller, and that is why we talk about balls. So balls in R, in L, sorry. So it's a generalization of the previous step in which we just considered C and DR. Now we go for L and BR. Here is, I mean, by this proposition, which is not difficult indeed to prove, we can generalize the previous proposition. Previous, I mean, from the last week. Here on Z, I'm sorry, on C, the inner product is Z times W bar, just Z W bar. And when we have AN ZN, we have the combination AN ZW bar N, which is well defined. In a Hilbert space setting, the inner product is ZW in L. And we can do the same. I mean, it's a complex number. We can do exponent N and multiply by AN. And if you have a polynomial with positive coefficients, so if P of Z or P of X is given n from 0 up to n, AN, ZN, the only restriction is that these are positive. Well, we can define K, P, ZW to be n from 0 up to n. What happened? AN, inner product of ZW exponent n, where here Z and W are elements of a Hilbert space L. Well defined. We want to prove this is positive, but it's kind of trivial because we saw before that the mapping, it sends the pair ZW to the inner product of ZW. This is positive. It gives us the Gramian matrix, and the Gramian is positive. We saw this before. And then the short product comes. If you have two positive matrices and you multiply them by short product or component-wise product, what you obtain is also positive. So as soon as we see that this mapping is positive, we immediately conclude that ZW exponent 2, exponent 3, exponent K, any K is positive. And then we multiply by positive coefficients and add them up. So immediately we get the sum, or Kp is positive. Nothing new in it, except that when we compare with the previous case, the reasoning is the same. The difference is that we replaced C, which is a Hilbert space, by an arbitrary Hilbert space. So on an arbitrary Hilbert space, we can define Kp by this formula, which is something positive, appealing to more theorem. So we can talk about H of Kp. So this RKHS exists. And what can we say about its element? So the next proposition, most of them we know. Oh, what happened? Do you see my screen? I don't see myself. Okay, you should see it now.
Looks good.
I can see this. Yeah.
Yes.
So this proposition, we know most of it, but there is one ingredient in it which is probably new. L, a Hilbert space. N is a positive integer bigger than or equal to 1. And Kn, K index n, defined on L times L with values in complex number by the formula we saw before, Kn Z n W is ZW exponent n. In other words, we just consider the monomial x to the power n. These are our assumptions. Then RKHS created by this contains, that's the purpose of this proposition, contains all functions G from L to C that can be written as a linear combination of products of n functionals. Of course, when we talk functionals, when everything is bounded, maybe I add here bounded functionals. So any you consider the dual space. So you have L, the space. So you have it's dual too. So dual consists of elements. F is in L star. So F is defined on L with values in C. You consider any n of these F1, F2, Fn in L star. You multiply them together, so they are arbitrary. F1, F2, up to Fn. That's a function, call it F. This is in H of Kn. And of course, I mean, I talked about linear combination because if a combination like this is in HKN, and you form another combination, then the sum with arbitrary coefficient is also is in this space. So the important part is this one. Why you multiply n functionals is in this space. The proof. Well, what are these F1 and F2? Remember F-Risk theorem. Says that if F is in dual, then there is, and indeed it's unique, but uniqueness is not here, needed here. There is a unique W in L such that F at each point Z is the inner product of Z and W. And sometimes we denote this by FW of Z. So it's a conjugate linear isomorphism between L and L star in this way. So it is enough to show that if omega 1 up to omega n in L are given, then F omega 1, F omega 2 up to F omega n, we multiply them together, is in H of Kn. This is our goal. We want to show this. How do we do that? This is again another occasion. We have used theorem 3.11 several times, but that's another point that we use it. It gives us a criteria, indeed two criteria, to see when a function given is in this space. So in parentheses, or I recall, very important result. F is in H if and only if there is a constant C such that f of x, f of y is less than or equal to C or C2 K, X, and Y. And even we had some more explanation about the minimum C that we can put there, but now this is enough for us. And this is one thing that we used before, but we use it again here. Another fact is that if you have 0 less than or equal to, say, matrices A1 less than 2, and also matrices B1 less than B2, but this is in the relation, partial relation that we defined before. A1 less than A2 means that the difference is a positive matrix. A2 minus A1 is positive, the same for B1 less than or equal to B2. This implies that 0 is less than or equal to A1 or B1. That's the short product, less than or equal to A2 or B2. It's very easy to prove, and I leave it as an exercise for the students. Of course, the main ingredient of the proof is, I give you a hint. The main ingredient of the proof is a short theorem which says that if S is positive and T is positive, then SOT is positive. And you can use this to prove this inequality. So why do we need this? Because we know this is a special case that we studied before, we saw before. And so it was one of the propositions that I proved, that F1 is in H of K1. K1 means capital N is equal to 1. I mean, here, when we go back. It's a very special case, but important when we studied before here. N equal to 1, just K, Z, and W is the inner product of Z and W. We saw that this is positive, and also each functional is there. So we saw this before, and the same for F2, the same for Fn is in H of Kn, and so it's time to use our theorem. The theorem I mentioned here as a recall. If a function is in the space, there is a constant such that this works. So there is a constant C1 such that F1x, F1y bar less than or equal C1k, which is K1, I can write K, X and Y. The same for F2 and the same for Fn. And of course, this is positive. Fn x, Fn y bar is less than or equal to Cn k, X, and Y. And these inequalities means that if you remove this to the other side, you obtain a function of X and Y is a kernel function. It means for all matrices, 1 by 1, 2 by 2, 3 by 3, all sizes, when you form the Gramian at any connection of endpoint, it is positive. It's a kind of huge restriction which is hidden in this little inequality here. But knowing this, now it's time to apply the box formula here. If A1 is less than or equal to A2, all of them positive, the same for B1 and P2, then you can do the Schur product. And do the Schur product to this, to the second one, and up to the last one. If you do the Schur product, you immediately see that by exercise. We have 0 less than or equal to component by component. So F1x, F2x, Fnx, which I called f of x. And then F1y, F2y, Fny is f of y bar less than or equal to C1, C2, Cn. I think above I wrote C1 squared. So let's keep the same notation. It really doesn't matter, but when we talk about the optimal value, it is important. So here we have C squared, where C is C1, C2 times Cn, and Kxy times Kxy times Xky n times. So we obtain this still in the language of kernel functions. This is less than or equal to this. One more time, but that famous theorem, by the theorem 3.11, we conclude that F is in the space H created by Kn. And also something about its norm, which is controlled by C, but I don't need that here. What I needed, I just wanted to show that if you multiply n functionals, you obtain an element of HKN. Special case. when your L is Cm. In this case, two elements of L, Z is equal to Z1, Z2 up to Zm, and W, W1, W2 up to Wm. It's okay to write it this way, but if you want to remove the bars later on, you can put the bar here. And Fw, F index W at point Z was the inner product of Z and W in Cm. It's just W1 times Z1 plus W2 Z2 plus Wm Zm. It's a polynomial of degree 1. True. And therefore, K n Z and W, when you form the multiple of this, would be W1 Z1 up to Wn Zn to the power n. And now what does the proposition tells us? What are the elements, some of the elements of HKN? It says that consider n bounded functional on Cm. You do not consider here all the functionals. I just consider some of them, but then thanks to the linear combination, we will see that we obtain at the end all the elements we are looking for. Just consider these elements, F, EI. EI is the canonical basis. So FEI evaluated at Z is just ZI. EI is 0, 0, 1, and this is just the ice place. So just FEI, and then you can see the n of this. So F is equal to F EI1, F EI2, F EIN. Repetition is, of course, allowed. In the theorem, we didn't say that F1, F2, Fn are distinct. No, it can be repeated. And when you evaluate F at the point Z, you see that it's of this form, Z1 to some power, Z2 to some power. And the power is the number of times that E2 is repeated here, up to Zm to another power, with the restriction, of course, how many times? N times. With the restriction that J1 plus J2 plus Jm is equal to N. That is because theorem tells us that multiply N of them together. And therefore, we see that this is a monomial of degree N. And when we consider all combinations, we see that polynomial of degree precisely equal to n belongs to H of Kn. In this case, this is a special case. This is a finite dimensional case. We can go further and do a bit of work to show that there is no more. These are all of them. And now we go one step further more. As before, we consider power series. So P of X or P of Z, sum n from 0 to infinity, a n x n, a n positive, and the radius of convergence as before R2 strictly bigger than 0. R can be plus infinity too, but it can be finite. And as I said before, usually we normalize it such that either R is equal to 1 or R is equal to plus infinity. It can be transformed into these two cases. And Kp that we consider here in this ball, note that in previous case, something that I should have highlighted. I highlighted at the very beginning of the talk today. This is the special case. Recall, where is that here? Here it is. Here, as you see, X is equal to L, the whole space. When we have a power series like this, we cannot do that. In this case, Kp, which is defined to be the sum n from 0 to infinity, an, well, I should have add 2 points, Z and W, is ZW in L, exponent L. Our X is a ball of radius R inside L, because otherwise Kp is not well defined. The series is not convergent. Br is considered to ensure that this series is convergent. That is why our set X is different in this case. So this we need to keep in mind. So as before, we can, it's easy to see, we have seen this several times before, Kp bigger than or equal to 0. And what are the elements? Now it's easy for us to see what are the elements. It depends if an is 0 or not 0. If it's 0, then it kills this part and we cannot say anything about it. But if it is not 0, then we see that we have, I mean, the term ZW exponent n, an, I mean, is we found it lives there, it's not dead, and it's less than or equal to our KPZW. So all elements which are in this space are in this space too, or it's better to say all elements which are created by this kernel are in the space created by this space too, because of the product that we saw before. And therefore, previous proposition tells us that the elements of this are polynomials of degree precisely equal to the n. So this one would have all polynomials of degree n, provided that an is not equal to 0. So we can say, I mean, I write the theorem as this. I mean, the hypothesis, you know what it is. I mean, it's as before, as in proposition, and we assume the convergence. The important part is here for each n such that an is not 0, strictly bigger than 0. H of Kp contains, so we distinguish some elements, every function on Br that can be written as linear combination. Again, this part is trivial, linear combination, it's a space. The part which is non-trivial and it's based on the previous proposition is this part. Combination of what? Of n products of n bounded linear functions, which we call them polynomial on C. So any product of n bounded linear functional, and then you sum them up with different coefficients, but restrict them to the ball to avoid any divergence problem, then this is an element of our space. So it's a direct generalization of the case that we saw before for C. We can go a little bit further, consider on Cm, and even still go a little bit further and consider on an arbitrary Hilbert space for the most general case that we consider here. An example which is very important, and it's indeed the topic of this week of the focus program. Again, consider P of x is equal to 1 over 1 minus x, and from 0 to infinity xn. In this case, an is equal to 1 for n bigger than or equal to 0. So it satisfies the condition of the theorem, and the radius of convergence is equal to 1. So Kp of ZW is simply Z inner product W exponent n, or 1 over 1 minus ZW. If we hadn't talked for 2-3 weeks about this topic, and somebody comes and tells you, okay, I defined K by this formula, then just show that Kp is bigger than or equal to 0. It's not that easy. I invite you to try. Just forget about what we have discussed up to now, and directly proceed and show that 1 over 1 minus Z inner product W is positive. Just this. We did a lot. We did short theorem, and then we considered polynomial. We had the theorem 3.11 for the membership inclusion, and then series, and finally we could show something like this. So it's kind of long journey to arrive at this simple looking result, but it's a precious one. And this kernel gives us a space HKP, and it's called Tori-Arvesson space. And well, let me emphasize on B1, it's on the unit ball of L. And this is something that Michael will talk about it tomorrow in further detail. The only thing which we can immediately extract from the previous theorem, because an is not 0 for all values of n, we can immediately have this corollary. Immediately have a corollary that it contains the product of all functional, because all an are non-zero. The Tori-Arvesson space on B1 contains every function that can be expressed, so it can be written as a sum. This is trivial. We are in a vector space, so this doesn't matter. But sum of what? Sum of product of, instead of n, now I say finitely many, because it doesn't matter if you consider 1, 2, 3, 10, all of them, all of the coefficient an are equal to 1, non-zero. So finitely many. Bounded linear functions. Right. So product doesn't matter how many, but finitely many of functional, and of course we can sum them up. What happened? Special case. If L is equal to Cm, so our Kp ZW is 1 over 1 minus Z1 W1 bar up to Zm Wm bar. This is the inner product of Z and W. In this case, H of Kp contains what? All polynomials. Because bounded linear functionals, you consider Fej, it gives you Zj when you evaluate at Z. And it doesn't matter how many of them you multiply together, you can create any monomial that you wish and then sum them up. So it's all polynomials. All of the polynomials are there. And this is another difference between finite and infinite dimensional case. I didn't prove here, but I mentioned that in this case, in the finite case, yeah, here, when we consider n, it is true that I just showed that these multiples are in Kn, but it's indeed both ways. There is nothing else. I mean, just these products and then their sum. But when we go to infinite dimensional case, it contains, but there are more. In other words, all polynomials, call them P, is in HKP, but not equal in this case. So that's an important space, which is the topic of this week. And we saw Seagal-Bargman space. We can consider the general shading of Seagal-Bargman either on L or, I mean, if you have L, you consider an to be 1 over n factorial, and then P of Z is sum n from infinity an Zn is e to the Z. And so your kernel here, Kp ZW, is just e to the inner product of Z and W. And that gives you a kernel, which we know it's positive, and it gives, because R is equal to infinity, it gives this Siegel-Bartman space on L. And on CM, we already saw it before. So it's H of KP is Siegel-Bartman on L. Remember, R is infinity. And if L is CM, we saw the kernel has an interesting property, Kp of Z and W in this case. Z1 W1 bar up to Zm W bar M. We can write it as the product of Z1 W1 bar, Z2 W2 bar, Zn Wm bar. We can separate the value, the variables. Not usually the case. We can just do it in this case. And this is the kernel for the Siegel-Bartman space on C, one-dimensional case, the same as this one. So it's a product of one-dimensional Siegel-Bartman kernels. I repeat, not usually this is not the case, but thanks to the properties of exponential, we can do it. We can do it in this case. So this finishes chapter 4. I mean, lots of interesting results in this chapter. And I mean, we take a break and I continue with chapter 5, in which we talk about operations on kernels, how we can add them together, multiply together, or I mean, even do tensor product, and we see a lot of results comes out of this.